All right, 9.5, alkenes and alkynes. What are those? I know you're excited to find out. Let's see what we got here. Okay, so alkenes are any molecule that has a double bond in it here. And you can see there's several double bonds in this alkene here. And an alkyne has a triple bond in it. So those are different than our alkanes. An alkene has a double bond, and an alkyne has a triple bond. So let's get into that. Of course, don't forget your bond angles. A lot of things that have single bonds, if carbon has single bonds coming off of it, it's going to be a 109.5, 4 things coming off, 1, 2, 3, 4. If you have an alkene, generally, it's going to have 3 things coming off of it. Look at this carbon here, 1, 2, 3. And then alkynes generally will only have 2 things coming off of it, 1 and 2. So that's something to keep in mind. As you go through here, don't forget your bond angles and just count the number of things coming off of it, and you'll be good to go. Let's look at nomenclature of alkenes. We have, let me move this thing out of the way. We have 2 carbons in here, so it's F, and since it's got a double bond, it's called ethene right there. This one's got 3, so that's off of prop, and it's got a double bond, so it's called propene. There you go. Pretty simple, huh? Keep it rolling. The number of carbons, you want to number them so that the double bonded carbons have the lowest numbers. We've got to tell where that double bond is. You would not want to name this one starting with this carbon. You'd want to name it starting with that carbon there, because the double bond would be coming off of carbon 1. Structurals 1 and 3, structures 1 and 3 are what we call structural isomers, okay? So these have the exact same molecular formula right there. They have the same formula, but you'll notice this double bond is off of carbon 1, and this double bond is off of carbon 2, so that's why they're called structural isomers. If you look at 2 and 3, both of them have the double bond coming off of number 2, but you can clearly see that they have a different 3D shape compared to each other. Those are what we call stereoisomers when they really generally have the same structural formula, but their 3-dimensional look is different. And I'll get into more specifics on that of what we have. Here's the example of some stereoisomers. This is what we call geometric isomers. You guys have heard of these as cis and trans. Cis is nothing more than, you've heard of these with probably fatty acids, cis fatty acids and trans fatty acids. Trans fatty acids stack nicely, which can clog your arteries, and cis do not stack nicely, so they don't really clog your arteries too well. This is in vegetable oil, and this is in like animal fats. Although bad for you, quite delicious. So that's what we're looking at. So when we look at this, we want to look at the hydrogens on either side of the double bond. See how these hydrogens here are on opposite sides of the double bond? That's why they're called trans. And these hydrogens are on the same side of the double bond, which is why they're called cis. So that's something to keep in mind when we name these things. I'll show you how to do that on the next few slides, all right? We're going to do some nomenclature of larger alkenes, nothing crazy. This is 1, 2, 3, 4. This is butene. 1, 2, 3, 4. This is butene, and 1, 2, 3, 4. So all 3 of those were still considered butene, but you can notice that they are completely different structures or different 3-dimensional versions of the same molecule. So let's check it out how we name these things, all right? The first one is just 1-butene. Notice that the thing is coming off of the first carbon. The double bond's coming off the first carbon, so we call that 1-butene, if you will. The second one's coming off the second carbon, so it's called 2-butene, but you'll notice that the hydrogens are on opposite sides, so we have to call it trans 2-butene. Notice there's always a dash in between any letters and any numbers, so when you name it, make sure you keep that in mind. This guy, let me move this guy a little bit to the side. If we look at this guy, we have 1, 2, the double bond's coming off the second one, so it's also 2-butene, but the hydrogens are on the same side. They're both on top, so that would be considered to be cis-2-butene. So you can see it down there at the bottom, cis-2-butene, so something to keep in mind. Notice it's got like a kink in it, which allows them not to stack nicely. These guys would just keep alternating, keep going. These would stack nicely in your arteries, which is bad for your health. Okay, let's keep rolling. We're going to do some practice here. We're going to name this alkene. Watch the 3 steps I follow. 1, 2, 3, 4, 5, 6, 7. This is based off of something called heptene. 7 carbons. Heptene. Notice it's got the E because there's a double bond right there. Now, what carbon is that double bond coming off of? Looks like number 2. So if it's coming off number 2, we now know it's based off of 2-heptene right there. And then if it's not coming off of carbon 1, we got to tell whether it's cis or trans. So notice this hydrogen's on the bottom, this hydrogen's on the top. That's a trans. So I would call this trans 2-heptene. That's what we're looking at right there. Something to keep in mind when you go through. Let's go name a few more of these things. Here's another one. Look, 1, 2, 3, 4, 5, 6. So this is based off of hexene. Notice it's ene right there. And this one's only coming off of carbon 1, so we just call it 1-hexene. And whenever it's coming off of carbon 1, we cannot give it a trans or a cis name, so we just still call that 1-hexene. Nothing crazy. Let's see another one with cis or trans here. 1, 2, 3, 4, 5, 6. Based off hexene, again, 1, 2, 3. So this this double bond is coming off of carbon 3, so we're going to call it 3-hexene. And look, hydrogen on top, hydrogen on bottom, so that means it's trans. So that's called trans 3-hexene. That's nice. Okay. When we name alkynes, these guys right here, they are just going to be called like an ine instead of an ene. So we have 1, 2, 3, 4 carbons. So that's based off of bute. But instead of butane or butene, we call it butyne. Notice we call it 1-butyne because that triple bond is coming off of the first carbon. This guy right here, look at it, still has 4 carbons in it. Has the exact same molecular formula, but this is coming off of the second carbon, so we call that 2-butyne. Something to keep in mind, alkynes do not have cis or trans because they are 180-degree angles. There's nothing coming off of the carbon on either side of the triple bond. All right. Physical properties of alkenes and alkynes. They have very, very, very low polarity, which means that they are, let's just call them nonpolar. They only have London dispersion forces, which means they have a very weak grip on each other. Two molecules don't really tightly adhere to each other, but they will as the molar mass gets bigger and bigger and bigger. They're insoluble in polar solvents, but they are soluble in nonpolar solvents because like dissolves like. Polar solvents will dissolve polar molecules, and nonpolar solvents will dissolve nonpolar molecules. So that's what we're looking at there. They generally have lower densities than water. Means they'll float on water. And their melting points and boiling points and densities generally increase with increasing molecular mass. That's like London dispersion forces. The more protons and neutrons and electrons you get in there, the more those London dispersion forces hold them together. So that's something to keep in mind as well. All right, let's go over some addition reactions with alkenes. So what that means is we're going to add something into the alkene. What I want to point out to you is that when we add things to an alkene, it literally it'll get rid of this double bond, which frees up each carbon to have one more bond. Because remember, carbons want 4 things. 1, 2, 3, 4. We get rid of this double bond in the alkene, and it allows this carbon to have one more bond and this carbon to have one more bond. So when we have it with an A and B, the A goes to one side, the B goes to the other side of the double bond that was there before. A couple of examples here. Here's one with hydrobromic acid or hydrogen bromide. When we do it, it's going to break that bond. The H is going to go here. The Br is going to go here. That's what it looks like right there. Same thing happens with diatomic bromine. The bromine will go underneath this carbon. This bromine will go underneath this carbon. Notice they don't lose anything. They essentially keep these 2 bonds here. They're right there and right there. They just add a new bond underneath that carbon for a new chemical. All right, let's keep rolling. You can do it with water. We're going to do the same addition with water to an alkene. Just pretend that water is H and a hydroxyl group or an OH. So it's H and OH. And it's going to be the same thing. We're going to break this double bond here. The hydrogen is going to go underneath this carbon, and the hydroxide is going to go underneath that carbon, making this right here. So what that does, if you just want a broad example, or not example, a broad explanation of what happens, if you add water to an alkene in an acidic environment, you can make an alcohol. All right. Now this typical alkene is called ethene, and this alcohol is called ethanol, which is our grain alcohol. That's kind of the way it works. We can do the same thing here. Take water, add it to this guy right here. We're going to break this bond. We're going to leave a new bond here and a new bond here, which means a hydrogen could go here or a hydroxide could go here. That's in an acidic environment. But watch this. This is kind of cool. the hydrogen can either go on the left or it can go on the right. It just depends on which one attacks where, on which these things can be made. So these are actually isomers of each other because the hydroxide and the hydrogen are at different spots. All right, something to keep in mind. Let's keep it rolling here. Last slide, polymerization of alkenes. What we're going to do, we're going to do the same thing. We're going to take this alkene plus this alkene plus this alkene, and we are going to combine all of them together to make a polymer, which is a larger molecule made from smaller molecules called monomers. What we're going to do is we need to join this carbon, this blue carbon, to this red carbon. And in order to do that, we're going to break that double bond to give it a chance to have one more bond. So if I break that bond, that carbon can bond to that carbon. And if I break this bond, this carbon can bond to this carbon. And it just keeps on going. So that's how you make a polymer of all these things. It's like how fatty acids get made and all that kind of stuff. And that's pretty much it. So I'll see you tomorrow when we talk about benzene and its derivatives. So good luck. See you tomorrow.